Okay, today is all about the joy of translations. So, yesterday was reflections. Today's translations, both reflections and translations are called, what are they both called? It's like a popular movie. They're like cars that change shapes. Good. Well, yeah, they're not called transformers, but they're called transformation. Yeah. So, good. So transformations, more than meet your eye, dude. Okay. All right. So transformations, they're reflections and translations. Yesterday, a reflection was an isometry. Why did we call a reflection an isometry? Tell your neighbor why we called the reflection an isometry. Reflection and isometry. Yes. Look at all the volunteers. Yes. Maddie, go ahead. Yeah, it is like a mirror. Yes? Good, because the image and pre-image are congruent. That's what an isometry is. Now, I keep hitting that because that's a vocab term. It's a math term that we're going to start using in here. Like if I walk up to you and go, hey, is that an isometry of that? You should be able to go, yes, or duh, McCoy, no, it's not. Okay, if we're at the football field and I point out, oh, look at those goalposts. Are those isometries? Because that's what we talk about at the football field. Okay, you should be able to say, yeah, because they're congruent to each other. They're reflections. In fact, McCoy, they're reflected across the 50-yard line. That's pretty crazy. Okay, so those of you who play football, next time you want to distract someone at the line of scrimmage, just start talking about reflections in the goalpost. Okay? All right, can someone define what a translation is for me? What do you got? Grace?
So translation is transformation that moves points in the same direction.
Good. A translation moves points in the same distance in the same direction. So, like yesterday, a reflection we called a flip. Today, a translation is called it's like when you take a figure and you slide it. Okay? So yesterday the slang term was a flip. Today the slang term is a slide. So flip, slides, and the next one is going to be turns. All right. What are the properties of translation? Well, go for it.
Translation is an isometry, and translation doesn't change orientation.
Good. It's an isometry. Does not change orientation. Tell your neighbor what orientation means. All right, time's up. Volunteer, what's orientation? Someone new. Carson, I appreciate you raising your hand. Someone that hasn't participated, what's orientation? Go ahead, Hannah. So kind of the direction. Yeah, it does deal with direction. Yep. Good, the order. So you remember yesterday we talked about 3 points, maybe having a triangle. Okay, if we called those A, B, and C, and then when I reflected it, and I had, say, A prime, B prime, and C prime, okay, if this was my line of reflection right in here. All right, if I reflect those, notice here we go A, B, C. That's going counterclockwise. When in a reflection, it changes orientation. Well, today's a slide. So if I take this figure and rather than reflecting, if I decide to slide it a certain distance, and each of those points travel that same distance, okay, when I do that, does my orientation change?
You can't see it.
Oh, sorry. Thank you. Does my orientation change on that? No, it's going to stay the same. Okay, so versus a reflection where this moves over and orientation changes, when you're doing a slide, you're not changing orientation. Go for it.
Would you still put the prime because they're moving the original shape?
Yep, you still put your prime. So in this picture, it should be double prime because we do that. But yeah, you still have the prime because it's a pre-image to an image. Okay? Hannah, Priscilla, how are you guys doing back there? Good. What's a vector? Carson.
The distance and direction of a translation.
Distance and direction of a translation. Okay. All right, so I want to take a look at this, talk a little more about vectors. So on page 133, the distance and direction of translation can be expressed as a vector. If I have t to t prime, so that's dealing with this vector. Notice that's a ray right there. Okay, and then r to r prime. Oops. And then y to y prime. Those vectors show how far we've moved each item. In fact, if you connect these points, our original points of our pre-image, to our image, if you connect those points by vectors, you get this three-dimensional looking shape. Once again, kind of blurry up there. But it's the benefit of using the PowerPoint. You actually can see things without them being blurry. Yeah. All right. I want you to take a look at this problem right here. Okay? Explain to your neighbor what's happening going from M, or actually going from M to G. Okay, so Logan, what do you think? What's happening going from M to G?
It goes down 1 and over 2.
Doesn't go down 1 and well, are you talking about like from here to here?
Yeah, and then
Yeah, it's not quite that, no. So if I'm going from this point right here to that point right there. I like how you tried to relate it to slope, but I think I don't think you quite have the slope there. Go for it.
Well, I think it goes down to over 5.
Okay, so it goes down 2 and over 5. So if you kind of relate it to slope, which I heard a few of you say, yeah, it just means that I'm going to the right 5 and I'm going down 2. How many said something like that? Okay, that's what's happening with a vector. And you'll notice the way we show that is vector notation like this. Okay, we use these brackets that kind of look like the greater than and less than symbols. Okay, so using that, we go to the right 5 and we go down 2. Notice how we write the name of a vector. So these are all math symbols. Okay, so mg, if we're talking about a vector, we just put an arrow like that above it. Okay, it's like someone forgot the bottom part. Yeah.
So it's not a ray, it's just you forget the bottom line.
Yeah, when you're talking about a vector. Yeah, I realize a vector is a ray. However, when you're expressing it as a vector to show movement, we use this. Yep. All right. So this does not represent a coordinate. Make sure we're clear on that. This represents a vector. So everyone tell your neighbor to make sure they're clear on that. Especially the 4 people that I see kind of zoning out. You're like checking out I don't know what you're checking out. Some of you are just staring at the wall over there like you're looking at the algebra. So make sure your neighbor gets these 2 things. Important stuff for notation on today's assignment. Have them explain it to you, especially if they just fall asleep.
I was thinking like up 2 or 5, but then that won't work because you can do that analysis because G can go today.
Okay, wrap up discussion. We're going to move on to this example here. All right, you don't have to copy down the rectangle. I've got it up here for you. But it says you've taken this rectangle, you've translated it 3 units to the right, 1 unit up. You connect the points. We end up doing the translation here, connecting the points here. We end up with this cool looking cube, okay? Or this box. I guess it's not a cube, it's a prism there. All right. Number 6, describe the vector in example 1 using vector order notation. I want you to do that with your neighbors. And number 7, use the vector notation to describe the vector with an initial point at 1, 3 and a terminal point of 6, 1 using vector notation. I want you to answer 6 and 7 with your groupies there. Okay, so for those of you that were sitting out there just staring at it going, you said I get a minute and I have no idea even where to start. The first thing you should do is just start describing what's happening. So if I'm moving, I moved this original rectangle, how far to the right or left? How far? Yeah. I moved it 3 units to the right. Okay, so if I'm moving 3 units to the right on the x-axis, is that a positive or negative 3? It's a positive. So that represents a 3 like that. And then did I move up or down? Up. So on the y-axis, is that positive or negative? Positive. So that's your vector. Okay? So just out of curiosity, how many were confused on it? Like I didn't really know what to do. Okay? How many of you kind of guessed and you guessed right? Okay? How many know what to do now? Okay? Well, let's try number 7. You use a vector notation to describe. You start at 1. So if I had a grid, which just so happens I have one, and I put a point on that grid of 1, 3. That's my initial. So 1, 3. And it terminates at 6, 1. 1, 2, 3, 4, 5, 6, and 1. We'll call that B. What is my vector going from A to B? Grace? 5. So you went 5 units to the right, and you went down 2. So it's vector 5, negative 2. Now I'm hoping that we don't have to continually draw that out, right? How could you have figured that out without graphing it? Given point 1, 3, and wanting to go to 6, 1. Yeah?
You could subtract the 1, 3 coordinates from the 6, 1. So 6 minus 1 is 5, and 1 minus 3 is negative 2.
Okay, so you could subtract. How do you know which way to subtract?
You just from x to.
Go for it.
Coordinate 2 minus coordinate 1.
Yeah, coordinate 2 minus coordinate 1, right? Just kind of like your x2 minus, or y2 minus y1. So this is my terminal. That's where I end. This is my beginning. Okay, so if I subtract these, if I would have said 6, 1, and then minus 1, 3, 6 minus 1 is my 5, 1 minus my 3 is negative 2. I've got it. So we want to put that in vector. That's kind of another route to go. Some of you just kind of did it in your head there. You go, well, I know from 1 to 6 I'm going 5, and from 3 to 1 I have to go back or down 2. That's fine as well. Okay, any questions? Let's see how well you get it. I'm going to pass out your assignment while you guys are trying number 8 and 9 right here. Okay? If you want to reference your book, you can, but try those. Let's take a look at it. Refer to the diagram in example 2. What is the image of S under this translation? So if I'm at S and I go, what's that mean I'm doing? Left 3. So 1, 2, 3, and down 1 I'm at R. All you pirates out there, R. Okay?
Let's put the coordinate and not R.
No, we want to put R, dude. Come on. We're going to put R. Poor thing. Needs something to brag about. Okay, what vector describes T going to P? So if I want to go from T to P, you shouldn't TP, but, okay, T to P. Where am I moving? I'm moving positive or negative on X?
Wait, no.
So from T to P, positive, how far?
6.
Positive 6, and going up or down? Up, how far?
3.
There we go, 6, 3, vector 6, 3. Describe in your words the distance and direction of the translation represented by vector 18, 0. What does the 18 mean? Someone that hasn't participated yet today. One person that hasn't gone yet. Okay. Someone that has went. Carson.
Means that you go 18 units right,
18 units right and
0 units up or down.
0 units up or down. Okay, let's take a look at our assignment. On your assignment, we got example side and mixed side there. Raise your hand if you participated today. So if you're working on this and it says find a single translation that has the same effect as a composition. Composition means multiple. So we're going to translate a figure, a vector length of 2, 4, and then another vector of negative 3, 1. So for instance, if I had, say, a coordinate right here at the origin, and I moved that point, let's call it point A. If I moved it 2, 4, so 2 to the right and 4 up, it would now be there. Okay, and then I moved it again from that same point. I now go down 3, or excuse me, left 3, and up 1. It's now right there. So I move this vector, and then I go to there, right there. The question is, what would your, did I do? Okay. Yeah. You're going to always start at. I'm just starting. You could start anywhere. Okay. Yeah. Now I'm going to start here. The question is, what is the composition? So what would that length right there be? Okay. So that length is, using my picture, it's actually, I guess we go this way first. Negative 1, 5. Mm-hmm. How could we have gotten negative 1, 5 without using the picture? Yeah.
Could you add your x values and then add your y values together?
You could. You could take this vector right here, the negative 3, 1, and just add the 2 up. So 2 and negative 3 is negative 1, 4 and 1 is 5, and that tells you what the composition would be. Okay, so you shouldn't have to graph it every time, is the point. Okay, hopefully just tell you can add them. Any questions there? A good question there, Carson. So tonight, page 134, you should read about how to transfer a shape using matrices. You'll have your original matrix, your transformation matrix, which gives you your new matrix. Okay, that'll be part of your assignment there.